Hello everyone, and welcome to the 2024 Cannabinoid Conundrum webinar series. Today we will hear from Dr. Rebecca Wagner, Chemistry Research Section Supervisor at the Virginia Department of Forensic Science, on quantitative analysis method for THC isomers and biological matrices. Without further delay, I will turn things over to Dr. Wagner.
As indicated by the title of the presentation, I'm going to discuss the work that was performed to revamp our quantitative analysis method for cannabinoids in biological matrices to really address the more recent changes in cannabinoid use. So as a disclaimer, I am a paid employee of the Virginia Department of Forensic Science, and the opinions expressed in this presentation are those of my own. Before getting into the specifics of the method, I think that it's really important to have an understanding of the various driving forces that impact our testing in forensic toxicology. So the consumption of cannabis sativa is not a new trend. The history of cannabis reaches back several thousands of years, with historical references indicating use in Chinese, Indian, Russian, and Greek cultures. It is suggested to have both industrial and medical uses, which makes the plant rather versatile. Both the female and male plants exist, with the female plants being mainly used for drug purposes due to the higher cannabinoid concentrations. The cannabis plant contains over 500 different compounds and over 104 cannabinoids. Several cannabinoids within the plant have been shown to have potential pharmacological properties. So these phytocannabinoids, including cannabidiol, cannabinol, cannabichromene, THCA, and delta-8 THC, have been shown to have potential pharmacological properties. However, none have really been shown to have similar, if any, psychotropic properties of the most common cannabinoid that we hear of, which is delta-9 THC. In addition to the 104 phytocannabinoids, there are also several other tetrahydrocannabinol isomers that have been increasing in popularity over the past several years. So these isomers include the phytocannabinoid delta-8 THC that was shown on the previous slide, but also synthetically derived isomers including 6A10A THC, delta-10 THC, and in addition to these tetrahydrocannabinol isomers, other cannabinoid derivatives including things like THCO acetate and HHC have been found on the illicit market. When discussing the transformation of cannabinoids testing over the past several years, it is really important to recognize the driving factors that have caused this ever-changing climate that forensic laboratories have been facing over this pretty long period of time at this point. The popularity of these compounds really started to increase with the publication of the Agricultural Improvement Act of 2018, which is also known as the Farm Bill. The popularity of THC isomers and other derivatives really increased with the publication of the Farm Bill of 2018. This was effective December 20th, 2018, and that Farm Bill established really the framework for the legal production of hemp in the United States, with the removal of hemp from the definition of tetrahydrocannabinols in Schedule 1. It really defined hemp as less than or equal to 0.3% THC on a dry weight basis. And the intent was really to allow the expansion of industrial hemp production and use, but it had significant implications on forensic testing, as many of you know, in seized drug sections across the United States. Traditional field test kits would no longer work, and laboratories were now faced with differentiating hemp from marijuana at threshold concentrations, given the specific threshold noted in the Farm Bill of less than or equal to 0.3% THC. During the time of the 2018 Farm Bill, several states within the United States were also changing language concerning marijuana, including concepts of medical use, decriminalization, and also legalization. The Commonwealth of Virginia has a very long history regarding legislative changes around marijuana. So, as shown on this timeline, the first attempt in decriminalization in the Commonwealth of Virginia was 2015, which was actually a failed attempt. We tend to see that a lot with our legislation. The first attempt usually fails for a decriminalization, with subsequent years having success with the decriminalization. That same year, legislation was passed for medicinal use with an affirmative defense for the possession of CBD oil or THCA oil solely for the treatment of epilepsy. From 2015 to 2018, there was a significant lull in the legislative changes that we experienced. As you can see, since 2018 and that Farm Bill, several changes have occurred within Virginia. In 2018, medicinal use was expanded to any patient who could potentially benefit, as well as the approval of 5 companies to open medical dispensaries. Prior to this, it was not legal to purchase products for medicinal use, which is a slight conundrum if they were saying it's okay. In 2020, marijuana was decriminalized with personal possession less than 1 ounce, carrying only a civil fine of $25. Within that same year, the first medical cannabis dispensary ended up opening, and in 2021, legalization of marijuana occurred with personal possession of less than 1 ounce being allowed without fine. Also, individuals over 21 years old could now grow up to 4 plants per household. The decriminalization and subsequent legalization caused an explosion in the number of hemp-derived products within Virginia at various vape shops, convenience stores, and even mobile trucks, kind of like the ice cream truck. Products are variable and product labeling requirements are significantly scarce. So hemp and marijuana products, as you probably all know, come in several different shapes and sizes. They come in whatever matrix you could really imagine, from vape cartridges to brownies to gummies or even tinctures and sublinguals. The challenge is not only the lack of regulation, but based on legislation from the legalization, the Delta 9 THC concentration within the product had to be equal to or less than 0.3%, which did not account for any other isomer. This caused an increase in the Delta 8 THC market, as well as other THC isomers. And to minimize the number of products containing THC isomers, legislative changes effective in July 2023 attempted to address the proliferation of these products. The legislative changes included changes to the definition within the Code of Virginia and the removal of tetrahydrocannabinols from Schedule 1. The change in the definition of hemp expanded the definition from no greater than 0.3% to also include the contents that could have no more than 2 milligrams total tetrahydrocannabinol per package, or an amount of cannabidiol that is no less than 25 times greater than the total THC per package. The definition of THC was no longer only Delta 9 THC, but included its salts, isomers, and salts of isomers. Additionally, it clarified the definition to include any naturally occurring or synthetic tetrahydrocannabinol. The total THC content now included the sum of all isomers and their respective acids. Further language was added to indicate that marijuana does not include industrial hemp extract, or hemp products. As you can imagine, the legislative changes were of the greatest significance for both seized drugs analysis and toxicology. During these years of change, the toxicology section of the Virginia Department of Forensic Science began observing challenges associated with the analysis of Delta 9 THC in biological matrices. The Virginia Department of Forensic Science toxicology section has been testing for cannabinoids in biological matrices for several decades. The original methodologies, like many other laboratories, included the quantitative analysis using GCMS. In 2013, the toxicology section actually published a newly validated method for the quantitative analysis of cannabinoids using liquid chromatography, tandem mass spectrometry. The extraction required a milliliter of biological matrix and employed more of a liquid-liquid extraction with a 9:1 hexane ethyl acetate for the quantitation of delta-9 THC, THC carboxylic acid, and hydroxy-THC, as well as cannabidiol. So as the years progressed and several iterations of legislative changes ensued, the presence of delta-8 THC became predominant within the analytical testing. The problem was that the original validation did not evaluate THC isomers for interferences when the analytical method was developed because they really didn't exist within the realm of forensic toxicology testing. Like many laboratories within the United States, the chromatographic method developed and implemented in 2013 did not resolve delta-8 and delta-9 THC or exo-THC and delta-9 THC. The bottom two chromatograms are of neat standards. The chromatogram on the left is equal concentrations of delta-8 and delta-9, and with delta-9 eluting first. And on the right, you'll see a mix of the delta-9 and exo-THC. The top chromatograms are actually casework samples that presumably contain both delta-9 THC and delta-8 THC at different concentrations. The one on the top right appears to have a small shoulder on the right of the peak, presumed to be delta-8 THC. And then the one on the right has kind of a resembling at the top of a splitting peak that is presumed to be both delta-8 and delta-9 THC. A change in the chromatographic conditions was really necessary to be able to differentiate these two compounds. The change in chromatography meant full revalidation of the analytical method. In addition to the need of a new chromatographic method, the need for comprehensive testing for driving under the influence case types was of significant conversation amongst legislators. So the Virginia Department of Forensic Science, like other laboratories, previously employed a stop testing limit within the analytical testing scheme for driving under the influence cases. The department evaluates both antemortem and postmortem toxicology cases with a caseload of approximately 10,000 per year, and that is split about half for drivers and half for postmortem. For driving under the influence cases, blood alcohol analysis was the first analysis to be performed. If the blood alcohol concentration was greater than 0.1% by weight by volume, the previous analytical scheme would stop testing on the case and move to issuing the certificate of analysis. Well, the proliferation of cannabinoids and the request from legislators for more epidemiological data with this drug class really changed the analytical testing scheme for driving under the influence case types. So the new testing scheme, which was implemented in early 2023, including testing of blood alcohol content on THC for all driving under the influence case types. Given the anticipated 25 to 30% increase in cannabinoid testing and the proliferation of THC isomers in cases, the new methodology to chromatographically separate THC isomers and identify these isomers, especially delta-8 THC, was critical. The assistance of the NIJ grant funding really made this project possible. So in 2021, as everything was kind of all happening at the same time, we received grant funding from the National Institute of Justice for a project entitled Expanded Quantitative Cannabinoid Testing in Biological Specimens to Combat the Ever-Changing Cannabis Landscape. The research project consisted really of three different objectives. The first objective was to expand the traditional scope of cannabinoid testing in forensic toxicology laboratories to include phytocannabinoid constituents in plant material and metabolites that are used in consumer products. The second objective was to investigate commercially available stationary phase substrates and instrumental conditions to really increase the selectivity and mitigate ionization suppression, which is commonly encountered in the analysis of cannabinoids and biological matrices. The third objective was to develop and validate an automated sample preparation technique for the quantitative analysis of cannabinoids in biological matrices using liquid chromatography, tandem mass spectrometry. The validation was performed in accordance with ANSI ASB Standard 036, which is the standard practices for method validation in forensic toxicology. So to get really an understanding of the starting point for the method development, it is important to assess the previously existing method. We can at least start from somewhere, hopefully. The original LC-MS-MS method utilized 1 milliliter of biological matrix and was used to quantitate delta-9 THC and its hydroxy and carboxy metabolites, and it was also validated for the analysis of cannabidiol. The extraction, like I had mentioned previously, was an acidic liquid-liquid extraction with a 9-to-1 hexane ethyl acetate. And after rotation, centrifugation, the supernatant was then transferred to a clean test tube and evaporated to dryness under nitrogen at a temperature between 40 and 50 degrees Celsius. Some limitations of the method that were really focal points for us in the development of a new method was the lack of chromatographic separation between THC isomers, also the significant and variable ionization suppression that we did see in post-mortem specimens, and the required sample volume. If we could decrease from the 1 mil sample volume, knowing that this was going to be utilized on all case types, that would be highly beneficial. So for that new analytical method, we wanted to include at minimum delta-8 THC into the quantitative analysis analytical scheme. Other isomers and metabolites would be assessed qualitatively. The quantitative and qualitative targets are included on the table alongside their proposed internal standards on the slide. And the initial method development began with the instrumental analysis using NEAT certified reference materials, like any good new method development includes. Given the number of phytocannabinoids and synthetically derived cannabinoids, to have the potential to interfere with either the quantifier or the qualifier ion transitions of the target compounds within the method, a different approach from that traditional single column analysis for LC-MS-MS was taken. To assist in the evolution of isomers and structurally similar derivatives, including ones that we had no idea would even exist at this time point, 2 analytical columns were used for the development of the method. The first column would provide the conformation and quantitation, while the second column would be a different composition using different mobile phases to provide a secondary chromatography to ensure that no unidentified compounds were potentially interfering with the analytical response of the quantitative column. The best judge that I have to kind of explain this idea is how most laboratories are performing their blood alcohol analysis with 2 separate columns. Just that extra separate chromatographic separation to ensure that we don't have any potentially interfering compounds that are structurally similar. So the analytical column used as the quantitative column was an Agilent Technologies PowerShell C18 column that was 3 by 50 with a 2.7 micron size. And that column was maintained at 50 degrees Celsius during the analytical run. Mobile phase A was 0.1% formic acid and water, while mobile phase B was actually 80-20 methanol acetonitrile. The flow rate was a lot higher than what we typically have at 1 mil per minute, with a gradient elution for a total runtime of 12.5 minutes with that post-run. The conditions for the mass spectrometer were actually consistent for both methods with the exception of our retention time windows. So I'll show that to you in a couple slides. So for the qualitative column, the analytical column utilized was also an Agilent Technologies, but it was a PowerShell pentafluorophenol column that was a 3 by 100 column that utilized a column temperature of 50 degrees Celsius to kind of help assist in that separation, the chromatographic separation. Mobile phase A was 0.1% formic acid and 5 millimolar ammonium formate in water. And then mobile phase B was 0.1% formic acid in methanol. The flow rate was a little bit slower than the other column, which was 0.5 mils per minute, and it also used a slight-ish gradient elution for a total runtime of 13 minutes. So here are the tandem mass spectrometer settings that were utilized. We utilized electrospray ionization in positive ionization mode. During the development, we actually also investigated a multi-mode source to assess the differences in ionization between electrospray ionization and atmospheric pressure chemical ionization. With the source, we were able to flip between electrospray and APCI within the same ionization source, but we really didn't see any significant benefits noted using the APCI as a really superior ionization source over ESI for cannabinoid analysis. So one of the main decisions that we had to make was we do not have APCI or multi-mode sources on all of our instrumentation. And if there was no significant benefit to be had, there was really no point in the financial hardship that might be associated with buying new ionization sources for all of our instruments across our 4 laboratories. So the optimized mass spectrometer parameters are also listed on the slide here. And the instrument was operated using dynamic multi-mode MRM mode with the bolded ions that you can see being used as the quantitative ion transitions. So let's dig into what success we were able to have with our chromatography itself. So the optimized chromatography for Delta 9 is shown here on the left-hand side, with having the original chromatography on the right-hand side. So the top right is showing the coelution of Delta 8 and Delta 9, while that bottom right chromatogram is showing the coelution of exo-THC and Delta 9 THC. The left, like I mentioned, is our optimized pentafluorophenyl chromatographic method. And so with this chromatography, the first eluting compound is actually Delta 8 THC, followed by Delta 9 THC, and that last eluting peak is actually exo-THC. So we were able to nicely resolve all 3 of those rather challenging isomers. Between the 2 chromatographic methods, the only compound that cannot be differentiated is 9R Delta 7 THC and Delta 8 THC, which I'll get to in a little bit. But prior to sample preparation development, the desired working range was really established and evaluated using certified reference materials, hoping that we can reach our limits that we need to reach and then optimize the sample preparation and add the complexities of our matrix in next. So the desired working range was established for each quantitative compound within the proposed analytical method. And then during method development, the lower limit of quantitation for Delta 9 THC and hydroxy THC was evaluated at being 1 nanogram per mil. After sample prep and calibration ranges were established to be slightly different, where the Delta 9, Delta 8 THCs could really go from 1 to 100, where that hydroxy, which we really desired to be down at a 1 nanogram per mil, we could really only detect with the various matrices that we were trying to detect between 2 and 200 nanograms per mil. And then for the Delta 9 carboxy THC, we were between 5 and 500 nanograms per mil. As for the sample preparation techniques that we did evaluate, we had historical information regarding the performance of the liquid-liquid extraction that we had had online for several years. And we really wanted to evaluate alternative extraction techniques to assist in the ionization suppression that we were often observing in those postmortem blood specimens. Now, one thing to keep in mind for the analysis that we do, we don't separate out postmortem from antemortem. So we really try to encapsulate our analyses to be able to do both different types of case types within our analytical runs for efficiency purposes. So one sample preparation technique that we investigated was the solid phase extraction using the United Chemical Technologies Clean Screen THC extraction column, which many of you are probably familiar with. This used a 200 milligram bed mass and a 10 mil total volume. In addition to these columns, we used the UCT Screen THC columns and the UCT DAU Clean Screen columns. The UCT DAU Clean Screen columns are the columns that we predominantly use for our solid phase extractions within the toxicology section for other analyses. So we really wanted to investigate the ability to use the same types of columns that we were already using. The optimized solid phase extraction procedure still required 1 milliliter of biological specimen, and it also required a protein precipitation prior to the solid phase extraction. The method was optimized by evaluating blank blood, postmortem blood, and antemortem blood along with urine. And as you can see, this is a lengthy extraction procedure, hence the incredibly small text. Although it might provide more sample cleanup compared to our previously existing liquid-liquid extraction procedure, the exponential increase in the steps, the solvents, the consumables, while maintaining that 1 milliliter sample volume is really less than desirable for our laboratory. Another sample preparation technique that was evaluated was a supported liquid extraction. So the supported liquid extraction, or SLE, utilized only 0.5 mils of biological specimen and has significantly fewer steps compared to the traditional solid phase extraction, which right off the bat is really great. The Biotage Isolute SLE 1 mil sample columns were found to be optimal during our method development. We also evaluated the Biotage 2 mil sample columns along with other SLE products from various vendors. This included both the evaluation of natural and synthetic cartridges. During the evaluation of the cartridges, the naturally occurring cartridges really did provide the most reproducible data, along with providing the lowest limits of quantitation. The sample preparation really included the acidification of your 0.5 mils of biological specimen with 0.1% formic acid and water. And the samples were vortex prior to being added to the cartridge. After the samples are decanted onto the cartridge and allowed to incubate for about 5 minutes, after kind of slightly drawing the matrix onto the top frit of the column, 3 mils of ethyl acetate was added, followed by 3 mils of N-hexane. All of the eluate is collected and evaporated prior to reconstitution and analysis. And as you can see, the extraction uses less specimen for the analysis and has significantly less steps, reducing the amount of time spent on the extraction itself. But to really further evaluate the difference between the two sample preparation methods, we performed ionization suppression or enhancement experiments and also recovery experiments in blank blood and postmortem blood to really assess each one of these methods to see which one really reigns superior, especially focusing on postmortem blood specimens, because we knew with our traditional liquid-liquid extraction, that's where we were starting to see the most challenges with ionization suppression. So the table on the top of this slide shows the ionization suppression or enhancement noted with the solid phase extraction procedure in that dark green color on the left-hand side, and the SLE procedure in the light green color on the right-hand side. The postmortem samples selected were selected to be different consistencies of postmortem blood to be really representative of the variability in that matrix type. We know that not all postmortem specimens are created equal. And although the results were rather similar for the solid phase extraction and the SLE procedures for the ionization suppression, the recovery varied drastically. If you really focus your attention on lucky number postmortem sample blood 3, the recovery from the solid phase extraction was dismal, with only about 35% was the maximum recovery for all the targets, while the recovery was greater than 84% for all of the targets when extracted using the SLE procedure. So after selecting the SLE procedure as the sample preparation procedure to validate, an investigation ensued regarding the silinization of glassware. So you might be wondering why the silinization of glassware. During the development of the two sample preparation methods, an evaluation of the impact of glassware silinization was really performed. Initially, all glassware in every step of the process for solid phase and SLE was silinized, including the autosampler vials. The silinization of glassware significantly improved the instrumental response for hydroxy-THC and carboxy-THC. Unfortunately, it didn't bump up our delta-9 THC anymore, which I know most of you probably also struggle with. Once we did see that, hey, there was a significant impact, but I do not want to either purchase silinized glassware or silinize glassware for the rest of my life for every step of the process, we performed a stepwise removal of the silinized glassware and determined what critical steps there were to require to be silinized for the optimal performance. And the interesting thing was that we found, and I wasn't necessarily expecting it, that the very first step in each one of the methods was determined to be the critical step. So that's really the step where you aliquot your case sample into the test tube prior to acidification. Upon the completion of our method development, a method development summary was created along with a method validation plan. So this method validation plan was in accordance with ANSI ASB 036 standard, which is the standard practices for method validation in forensic toxicology. If you're not familiar with this document, it was published in 2019 as a national standard, and it is currently undergoing its 5-year revision. So make sure that this is a little plug to be on the lookout for that 5-year revision so that you can comment on those changes that are being made. So in that, the creation of the validation plan included all of the steps delineated or all of the experiments delineated on the slide. Within each component, the number of matrix sources, replicates, acceptance criteria were all delineated for each experiment type. This plan focused on the quantitative targets within the project. This will be the main focus of the remainder of the presentation, but I will leave some of the validation components out for the sake of time because there's just so much validation information. So I really just wanted to cover the key highlights of some of the things or interesting things that we found. For the quantitative validation, both the C18 column and the pentafluorophenyl column were evaluated against that quantitative criteria, recognizing that the PFP column would really serve as the qualitative verification, but we did want to test it to see what its limitations were, if any, in comparison to the C18 column. It is important to recognize that a qualitative validation was also performed for delta-8 carboxy-THC, delta-8 hydroxy-THC, 6A10A, delta-10 THC, and hexahydrocannabinol, or also known as HHC. The decision as to what additional THC isomers were really included in the qualitative validation was based on the data received from RC's drug section and the prevalence of those THC isomers. So we really wanted to only include ones for the time being that were of significance that had been seen previously. But for our interference study within the validations, several additional THC isomers, phytocannabinoids, and synthetic cannabinoids were also evaluated, which I'm going to show in detail later. So for bias and precision of the method, it was assessed by analyzing pooled blank blood, antemortem blood, and postmortem blood. Pooled fortified blood was prepared at 3 different concentrations, the low, medium, and high, and evaluated in triplicate over a total of 5 batch analyses, which is our pretty standard ASB 036 requirements. In addition to the evaluation of bias and precision within blank blood, the calibration curve was prepared in each matrix type to really evaluate the impact of that non-matrix match calibration. Our laboratory uses blank blood as our calibration curve, so we wanted to ensure that there was no impact on our bias and precision for our other matrix types, antemortem blood, postmortem blood, when using a blank blood source. The predetermined acceptance criteria for bias was plus or minus 20% for all 3 concentration levels. And then the within run precision and between run precision was acceptable with a percent CV of less than 20%. So I'm going to have a couple slides of a whole bunch of tables and numbers. So don't get too overwhelmed by the numbers, as this presentation and the slides will be archived so you can review them later. I wanted to make sure that you did have the data for this to see. But this table shows the bias associated with the C18 analytical column. All matrix types had bias values within the predetermined acceptance criteria of plus or minus 20%. There was no significant impact on the bias noted for antemortem and postmortem blood when evaluating against that blank blood calibration curve. And cannabidiol had the largest bias for all target compounds within the method. And the precision from the C18 column was also evaluated using both within run precision and between run precision assessments, which I'm going to show you now, which is even more numbers. The within run precision is shown in the table on the left, and on the right, we have our kind of between run precision. All target compounds were, once again, you'll probably have to trust me on this one, were within plus or minus 20%, but more significantly, they were less than 10% for all compounds and concentrations. The between run precision was determined for each compound at all 3 concentrations by combining the data from all 5 analytical runs and calculating the percent CV, which is shown on the right. The percent CV was within 8% for all compounds at the concentrations, which is less than that predetermined acceptance criteria of 20%. So then this is the C18 column, which is our quantitative column, but we actually looked at the data since we were collecting it anyway for the pentafluorophenol analytical column. So the table actually shows that the bias associated with the PFP column is really all within that predetermined acceptance criteria of plus or minus 20% of the target compound. There was really no significant impact noted on the bias for antemortem and postmortem blood again when evaluating against that blank blood calibration curve. Cannabidiol still had the largest bias for the target compounds within the method, which was following that same trend as the C18 analytical column. The precision from the PFP column was also evaluated with the within run and between run precision assessments. The within run precision, once again, is shown on the left, and the precision was calculated for each concentration within each batch with the largest precision from the 5 batch analyses displayed on the table. So this is the largest that we saw out of all 5 analytical runs. All target compounds were within the within run precision of less than 20%, but more significantly, they were all less than 9% for all compounds, with the exception of the high delta 8 THC, which had a percent CV of 50%, or 15%, I'm sorry, 15%, and our acceptance criteria was 20%. The between run precision was determined for each compound at all three concentrations by combining the data from all 5 analytical runs and calculating the CV. The percent CV was less than 10% for all concentrations for all compounds, which was less than our acceptance criteria. So in addition to bias and precision experiments, the sensitivity of the analytical methods was also evaluated. So the sensitivity was actually a pretty interesting experiment that we did perform. The estimated limit of detection and lower limit of quantitation were both evaluated during the validation. The estimated limit of detection was established to be an administratively defined decision point concentration. Our laboratory uses what we call a threshold control, and that is an administratively defined decision point that is 1/2 of the lowest calibrator concentration. But given the significant ionization suppression that was noted with the matrices, a total of 9 blank matrix sources per matrix type were evaluated for both LOD and lower limit of quantitation experiments. And we'll get to the ionization suppression data later. The lower limit of quantitation was established at 2 nanograms per mil for delta 9 and delta 8 THC, 4 nanograms for hydroxy THC, and 5 nanograms for carboxy THC. The evaluated LOD and LOQ were both performed over 3 analytical batches. So if we look at this method, the established limit of detection ended up actually equaling the lower limit of quantitation. The lower limit of quantitation ended up being 2 nanograms per mil for delta 8 and delta 9, really in our postmortem specimens, and 4 nanograms per mil for hydroxy and cannabidiol, and then finally 5 nanograms per mil for carboxy. During the assessment, we had several qualifier ion ratio failures that were noted with hydroxy THC. That was really the biggest note of significance as to why we really couldn't reach the significantly low concentrations that we were really hoping to reach. But we did notice that upon evaluation, the hydroxy THC had those failures at approximately 10%. And if we refer back to ANSI ASB 098, which is the standard for mass spectral analysis in forensic toxicology, since the relative intensity was significantly low for our qualifier ratio, it is allowed to change the qualifier ratio acceptance from plus or minus 20% to plus or minus 30%. So we reassessed the data for the hydroxy THC, and with that plus or minus 30% qualifier ratio acceptance criteria, and all replicates with the exception of 1 postmortem replicate evaluated for hydroxy THC on both analytical columns was within acceptance. So one really important thing to note is that we were unable to reach the lower limit of quantitation that we wanted to reach for postmortem specimens. We were able to reach it for antemortem and blank blood, but we did see that significant suppression or impact with the postmortem specimens on our lower limits. And because of that, we did end up, when we implemented the method, have to change that lower limit of quantitation for postmortem samples to be slightly higher than our antemortem specimens. So ionization, suppression, and enhancement, ionization, suppression, or enhancement was evaluated. We used the post-column or post-extraction fortification of samples compared to our NEAT standard. So the post-extraction fortified samples were prepared by extracting blank blood and fortifying the eluate after sample preparation, since we're doing an SLE. And we do this, we fortify it prior to evaporation of the samples, and then we evaluate by comparing the target compounds and the internal standards as well. two different concentrations are assessed. We actually do it in duplicate determinations per matrix source, and then a total of 10 matrix sources per matrix type. So considering a matrix type of postmortem blood, antemortem blood being another matrix type, and blank blood being another matrix type, and then finally urine for qualitative assessment, the ionization suppression or enhancement was noted to be significant if it exceeded plus or minus 25%, or the percent CV was greater than 20%. And as you can imagine, with cannabinoids, ionization suppression was observed. So we did see it at different rates for the different columns, which would be expected. And I have the samples that were greater than plus or minus 25% suppression or enhancement highlighted in blue. So the C18 column actually demonstrated more ionization suppression than the pentafluorophenol column for all matrix sources, with the exception of blank blood. Blank blood always works so much better than everything else. So the PFP column data will be shown next, but overall urine was significantly suppressed for all matrix sources. And as I mentioned, these values that are highlighted in blue exceed that predetermined acceptance criteria. Because of the significant suppression that was noted in our antemortem, postmortem, and urine, that is why we increased the number of matrices. We tripled them for the lower limit of quantitation experiments. So this is the pentafluorophenol column, ionization suppression or enhancement. And as you can see, we did see pretty significant suppression, but not nearly as much as the C18 column, especially in the urine specimens. There's not nearly as much blue on the slide, which is indicative of not as much suppression. Also, our sample of our carboxy-THC and antemortem blood at that cusp of 123%, not necessarily being enhancement, but the percent CV was actually greater than the acceptance criteria for that one. So we did have to indeed triple everything for the C18 and PFP column. And if you're like me, you might be wondering, well, why don't you just use the PFP column as your quantitative column, as opposed to the C18, which showed more suppression over the various matrix types? And we found that the PFP column, although it could hit the lower limits of quantitation, it was much more variable and sporadic, especially with the postmortem specimens when talking about even questionable chromatography. So it was not nearly as robust as the C18 column, and therefore the C18 column did maintain as that quantitative column. So the really important thing to discuss is interferences. So the table shows some of the cannabinoids that we evaluated during this assessment. As you can imagine, this is an expanding list as new cannabinoids are discovered and solicited in various cannabis products. The cannabinoids were evaluated on each analytical column to develop really a full picture of the analytical procedure. An important thing to note here is that you should always thoroughly evaluate the certificate of analysis of your certified reference materials that you're purchasing. There are some instances where this certificate will note that other cannabinoids may be present in the CRM other than the intended cannabinoid that you're looking for. This might send you down a rabbit hole. And so when you identify a potential interferent, so you want to make sure you look at those certificates of analysis, but it's also important to assess the impact of the potential interferent. For example, delta-9 THC acetate, which has been identified in many instances as a prodrug for THC, is significantly unstable and will quickly break down to delta-9 THC. This has been observed with both GC and LC analysis, but really back to the matter at hand is what is truly interfering or potentially interfering with this method. So this table really summarizes the interferences study for just the cannabinoids. We evaluated a lot of other things, but the first column is what compound we are assessing. The middle column is the PFP column, and the right-hand column is the C18 column. So when assessing the interferences, we're evaluating the retention time, instrumental response, and both the qualifier and the quantifier transition windows, and general peak shape. For the PFP column, the only real interference noted was the delta 7 THCs, and we noticed that the delta S or the 9S delta 7 co-eluted and had a similar qualifier ratio as the delta 9 THC. While in the 9R delta 7 THC had the same retention time and qualifier ratios as delta 8 THC. When we looked at the C18 column, we have noted slightly more potential interferences than the PFP column. For the C18 column, delta 9 THC and exo-THC co-eluted, and both delta 7s, the 9R and 9S, as well as delta 8 iso-THC co-eluted with delta 8 THC. I know that this is a ton of information to take in a really short period of time, but to really break it down for you, when using the two-column system, the only compound that we have currently identified that we cannot distinguish is delta 8 THC from 9R delta 7 THC using both columns. This table right here really shows the benefit of having two columns for the analysis. And the validation of this method presented several twists and turns, just like the ever-changing landscape of cannabis within the United States. But before we go today, I wanted to discuss one other notable item that was gleaned from this validation. So this is a tale of the inconsistent interferent that could never go away. When performing method development or validation, we always run a negative control, just like running our negative controls for casework. During method development, our negative control was always just that, negative. When we started the validation, we made sure to order plenty of SLE cartridges that we could perform the entire validation without delay. Well, from the order, we discovered an interfering peak in the qualifier transition of delta 8 THC. It was a small peak, and sure, it was the qualifier and not the quantifier, but the interferent proved to be pretty mighty. Upon dissection of the entire analytical method, it was determined that that interferent was actually present in the cartridge itself. The problem: how do we remove it? After partnering with a vendor and analyzing dozens upon dozens of lots of cartridges, we noticed that more lots than not, lucky us, had the interferent, and the ones that had them to varying degrees. So what does this mean for us? As you can see on the lower chromatogram, the impact of the interferent on the delta 8 qualifier. At the low end of the calibration curve, the interferent was contributing enough to the delta 8 qualifier that the qualifier ratios did fail. What is the resolution, you might ask? Well, the way that we had to handle this situation, and as we kind of alluded in other situations, like post-mortem, was that we had to identify it, hope to remove it, but we would only report out qualitative delta 8 THC and raise that threshold to ensure that the interferent is not impacting the analysis until we were able to get interferent-free columns and perform a verification of our quantitative validation. If the interferent is present, you are fine to qualitatively evaluate, but if the interferent is not present, you can quant away using the validated lower limit of quantitation. So in summary, overall, the project was a success. It would not be considered research if we didn't discover new things and have struggles along the way, but we were able to validate a new method that now utilizes less sample volume than before, takes less time to perform than before, And we really have to note that the biggest thing is that now we are able to confidently separate out delta 9 and delta 8 for reporting and all of the other isomers, which we could not previously do. So, although there are some growing pains associated with implementing new methods and validating new methods, specifically cannabinoids, we are much better off now than where we were previously with our old method. So, as some acknowledgments before we can entertain some questions, that none of this work would really be possible without the help of our team. Both Ali and Denise worked on this project in various capacities. And our toxicology program manager, Jim Hutchings, and our director of technical services, Alka Lohman, spent countless hours listening to me talk about the struggles associated with cannabinoids. And finally, this work would not be possible at all without the funding received by the National Institute of Justice. So thank you very much for your time today. And please reach out to me if you have any questions or there are any questions that you have that I can answer now.
Great. Thank you, Dr. Wagner, for the great presentation. I'm Catherine Bollinger, a forensic scientist at RTI, and I will be your moderator for this session. So our first question from the audience we have is going to be related to the interference you were talking about with SLE. The question is about whether you tried a pre-wash step to remove the interference before SLE.
So we did try a pre-wash step, and we were successful with the pre-wash step to remove the interferent. The problem that we had as an agency with implementing a pre-wash step is that it's not under the manufacturer's conditions or kind of suggested specifications. And having the assurance that the column was completely dry after we did the pre-wash and how long it was stable for or what changes were made to that column. So we did try it. It did work, but not something that we were willing to risk at the current moment.
Great. Thank you for that, Dr. Wagner. Our next question from the audience is, did you evaluate the method's suitability for analysis of serum and urine specimens?
So we did not look at serum because mostly we don't receive too many serum samples ourselves, but we did assess urine. Our laboratory qualitatively reports urine, so we did evaluate urine for qualitative purposes, and it passed the validation.
Okay. I think we've another one we had is about detecting stereoisomers in the method, if you were able to do that in the method you had with stereoisomers.
So we can detect the stereoisomers. We did not include those within the method itself with this rendition because that was not necessarily something that we were seeing, but we can separate them.
Great. One quick question that we can probably get in is there was an asking about software that was used to process the validation data.
So what we do is we export all of our validation data. We have Agilent instrumentation, so we export the Mass Hunter data into CSV files. And then we have actually written macros within our section to then take from the CSV files and auto-populate into our Excel spreadsheets for processing.
All right. Well, thank you, Dr. Wagner, and thank you for everyone that's been here today. Unfortunately, we are out of time, so please feel free to reach out to the presenter for any additional information or if you have any other questions, and we'll see you at the next presentation.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.